talk proper, I'll start talking about this topological holomorphic GL twist of 5D maximally supersymmetric Yang-Mills, n equals 2 Yang-Mills in 5 dimensions. And by topological holomorphic, I mean, in 3 directions of the theory, operators are independent of, coordinates in those 3 directions. And by holomorphic, I mean operators depend on a z coordinate on the Riemann surface in the other 2 directions. And by a GL twist, I mean that if you reduce this 5D twisted topological holomorphic twisted theory, you get the 4D GL twist that's completely topological in all 4 directions. This idea whereby you have a mixed twist of a higher dimensional quantum field theory that reduces to a quantum field theory that's topological in more directions is something which you can, aside from a hard computation of the quantum field theory itself, you could see this from string theory as, low volume theories of branes in a background where you have this cotangent bundle that's in the orthogonal directions to the brane and a normal bundle that is a subspace of this cotangent bundle, and then having the scalar fields in the world volume taking values in this normal bundle and therefore cotangent bundle, and the number of directions in which it gets twisted from a scalar field to one form. So from this sort of understanding from string theory, you could see that you could start off with theories in high dimensions that have a mixed twist. And as you go down in dimensions, the twist starts to get more topological in more directions. So in this particular case of an example in 5 dimensions, we have 3 dimensions which are topological, 2 dimensions which are holomorphic. And essentially when it means it's holomorphic in those 2 directions, you can see that the observables that we are interested in and computations we're interested in do not depend on the Kähler structure of those 2 directions. And so we could rescale them. And if you go down in 1 dimension, it becomes purely topological in 4 directions. So I've said a bit about this, but we'll see a bit more when we get to the main body of the presentation. And then I will talk about this 3D Toda theory. So this is like a 3-dimensional analog of 2-dimensional Toda theory that we know so well. The usual 2-dimensional Toda theory, which gives us a W algebra symmetry and representations of W algebra symmetry. But in this case, we have a 3-dimensional Toda theory. Okay. And where this Toda theory comes from is that it's the boundary theory of 4D Chern-Simons in which we embed into this 5-dimensional topological holomorphic maximally supersymmetric Yang-Mills. And then we will talk about this open topological sigma model on Bogomolny moduli space that we get by reducing equivalently in 3 directions of the 5D Yang-Mills theory. And then from comparing the Q cohomologies of the master theory, we end up getting this 3D, 2D correspondence between the 3D Toda theory and the 2-dimensional sigma model on Bogomolny moduli space. And then we will conclude our talk with the results that we have obtained and some interesting future work that we intend to embark on. So just as an introduction and sort of in some sense a motivation of why we want to study this. So if you look at the AGT correspondence, okay, this is a very well-known correspondence. It's been around, for 11 years now, I think, 2009 to now it's 11 years. And essentially it relates 4-dimensional n equals 2 gauge theory in its initial incarnation, of course, the Nekrasov partition function of n equals 2 gauge theory, and then conformal blocks of Toda theory, right? And so generically, it relates 4-dimensional n equals 2 gauge theory and 2-dimensional Toda theory on the Riemann surface is sigma tilde. So among other approaches to understanding this correspondence, it is also known that the AGT correspondence can be understood in terms of this relationship between Hitchin's moduli space, okay, which is the phase space of the Coulomb branch of n equals 2 gauge theory in 4 dimensions, and W algebra representations, which are representations coming out from Toda theory. So this was done by Nekrasov and Witten in 2010 in this paper called Omega Deformation, Branes, Integrability, and Liouville Theory. So, I mean, this is one approach. There are several approaches that tell you, the sort of the equivalence, why AGT correspondence is true. Mathematically, it sort of relates equivalent cohomology of the modular space of instantons with, modules of W algebra. So there are many ways of sort of understanding the AGT correspondence, and this is one way in which you can see there's a correspondence between 4D n equals 2 gauge theories and 2D Toda theories. Okay, so this was done by Nekrasov and Witten. So in this work, we present an analogous relationship, okay, but it's between the moduli space of solutions to the Bogomolny equations and representations of a novel W algebra arising from a 3-dimensional analog of Toda theory. So what we would have in the end, we would derive a Lagrangian that looks like the Toda theory Lagrangian, but it's valid in 3 dimensions. Okay. And as mentioned, this 3D Toda theory is a boundary dual of 4D Chern-Simons. So the 4D Chern-Simons theory that Costello, Yamazaki, and Witten has been studying for in the past 2 years. So we would define them on a form manifold with boundary, and you can see that we can show that if we start from a master theory in 5 dimensions, we would be able to get this 3D Toda theory at the boundary of 4D Chern-Simons. So yeah, so that's possible because we can embed the 4D Chern-Simons in a partially twisted 5-dimensional n equals to 2 super Yang-Mills, as I mentioned, and partially twisted in the sense of holomorphic topological twist. And we define it on a manifold with corners. Okay. And because it has corners, then we are able to do a different reduction in a different direction. And then we can also show that this 3D Toda theory is dual to an open topological sigma model on the Bogomolny moduli space. Now, this sigma model is an A-twist sigma model. So we would have Lagrangian branes, and that gives us some interesting mathematics. So essentially what we will be doing in this paper, so it's a very straightforward procedure. So the main body of the paper will just, detail out the computations and some of the details of the computations. So we start with 5D maximally supersymmetric Yang-Mills on a 5 manifold that looks like this. Okay, so we have an interval, an R and an R plus. This gives us the corner and cross a Riemann surface. So the theory is topological in these 3 directions, holomorphic in this direction. Okay, so we could recast this twisted theory, the Lagrangian of this twisted theory, as a Q-exact term, and then a topological term that localizes onto the boundary. Okay, and when it does localize onto the boundary, if you're looking at Q cohomology, the spectrum of Q cohomology operators and states of the 5D theory, we will see that it localizes onto 4D Chern-Simons, at the boundary of R plus, where it's the origin of R plus. Okay, so that's our boundary, the first boundary for 5D Yang-Mills, and then we get 4D Chern-Simons on this guy here. Okay, and then because the theory is topological in these directions, we can also shrink I down, and there are boundary conditions at the 2 ends of I. Essentially, non-pole boundary conditions are admissible. They preserve the correct amount of supersymmetry, and then when we shrink away I, we would get a 3D Toda theory that lives on R cross sigma. Right, this is where we get the 3D Toda theory from one side. So this is one way in which we come down to 3 dimensions. So then on the other hand, so as I mentioned, it's holomorphic along these directions, which means it doesn't depend on the Kähler structure of sigma, and therefore we could scale sigma up and down. And it's also topological on R, which means together R cross sigma itself, we could rescale this factor in 3 directions down. And in the end, when we do that, we actually get a 2D A model whose worldsheet is a strip like this, a semi-infinite strip like this, and the target space being a Bogomolny moduli space on R cross sigma. Okay, so this reduction here is something which has been used in many places. It was first done by, I think, Harvey and Moore, Vafa, Sadov, Johansson, Witten, and Kapustin used it, for using 4D supersymmetric Yang-Mills and 4 Yang-Mills, and then reducing it on a Riemann surface, getting a 2D sigma model on another Riemann surface, and then getting geometric Langland's duality from S duality. So it's the same kind of procedure. So essentially, we're just scaling down, different parts, scaling up, scaling down different parts of the metric, keeping terms that survive the scaling, and then integrating out fields which become auxiliary as a result of this rescaling. Okay, so we have this correspondence, as we mentioned here, between 3D Toda theory on this and 2D A model on this. And so the equivalence of the Q cohomology of physical states that descends from the master theory itself in 5 dimensions would then imply that modules of 3D W algebra, which is the states coming up from the 3D Toda theory, the Q cohomology of states coming up from 3D Toda theory, okay, defined on R cross sigma, are also modules for the quantized algebra of certain holomorphic functions on the moduli space. Okay, so this part here is not so clear from just looking at the A model. Okay, essentially, if you look at the Q homology of states of the A model, there are certain strings which can be shown to be modules of certain types of strings with different Lagrangian branes, essentially canonical co-isotropic branes. They're space filling strings that are between these 2 types of branes will act on strings that are suspended between different kinds of branes, and you can see this module structure coming out from it. And if you quantize the strings with the same space filling branes on both ends, they actually correspond to They correspond to an algebra of holomorphic functions acting on that survive, that live on the Bogomolny moduli space. And this is where we get the segment of the modules of the states of the A string being modules for the quantized algebra of holomorphic functions on MB, and that correspondence with the modules of 3D W algebras coming from the 3D Toda theory on the other side. Okay, so this is sort of the punchline, the mathematical sort of consequence of this physical study of partially twisted gauge theories in higher dimensions and then their different reductions. This is the mathematical punchline, and of course the physics is, you know, a 3D Toda theory being equivalent to 2D sigma model. Okay, so this talk is based on a piece of work with my postdoc and student, and it's we're hoping to get it out on the archive next week. Yeah, so it's of the same title as the talk. So 4D Chern-Simons theory as a 3D Toda theory and a 3D 2D correspondence. Okay, so let's get to the talk proper. I mean, so the main body of the talk. And let's discuss this topological holomorphic GL twist of 5D maximally supersymmetric Yang-Mills theory. So if you look at 5-dimensional maximally supersymmetric Yang-Mills theory, involves fields which transform as rep SO5. So we are working Euclidean signature. So that's why we are replacing the Lorentz group with an SO5 group. And then with the R-symmetry group, which is SO5 too, R-symmetry group. And so you have the gauge fields, the 5 gauge fields that transform in the 5 of the Lorentz or the space-time group. And then you have these scalar fields here, which transform in the 5 of the R-symmetry group. And of course, you have 16 supercharges for n equals to 2 in 5 dimensions. And we have spinors which transform in the 4 and 4 of SO5 cross SO5R. So of course, we can understand this from string theory. I mean, this is just the world volume theory of a D4 brane. And there are, of course, you know, a D4 brane is half BPS, and then we will get 16 supercharges in the world volume coming, you know, which is preserved from the background of 32 supercharges in type 2A string theory. And we have these 5 scalar fields that determine the 5 spatial directions orthogonal to the D4 brane in 10-dimensional space-time type 2A string theory. Okay, so it's a very nice action. We have studied this many times, and it looks very nice and neat like this. So for simplicity and for general, I mean, to say very concrete results, let's just choose G equals SUN as our gauge group in whatever follows in our discussion. Okay, I'm sure most of you are familiar with the Lagrangian already for 5D Yang-Mills. Okay. Now, so we want to do a partial twist. So what does this mean? So let's take the 5D world volume to be M equals V cross sigma. V is a 3-manifold, right? And sigma is a Riemann surface. So we want to twist the theory in such a way where it's topological on V. Okay, so we want to have a topological twist of this D4 brane world volume along V. So what is the usual prescription of twisting, you know, as you know, elucidated a long time ago by Edward Witten? So this amounts to redefining the space-time group in 3 directions to be a diagonal subgroup between the space-time group and the R-symmetry group. Okay, so schematically it's written like this. So the procedure itself just involves looking out for indices on fields which have R-symmetry indices in the 3 directions, 1, 2, and 3, and replacing them with space-time indices. Okay, so if you look here, the R-symmetry indices are all hatted. They're hatted. Space-time indices are not hatted. So what you're going to do is that if, for example, you look at the 5 scalar fields that we have, which transform in the 5 of the SO5R. Okay, so we're looking at just SO3, so there's 3 of them. So if you unhat them, if you unhat these 3 indices here, so they all become phi 1, var phi 1, var phi 2, var phi 3, and you notice that they form a 1 form on V with 3 components. Okay, so that's where you can understand that the theory has been twisted along V in a topological sense. So this twist, and by supersymmetry, I mean, I've skipped some details because of time constraints, but in the past 2 papers, we have shown this very clearly in some of two papers that we wrote on related topics regarding this partial twist in 5 dimensions. So supersymmetry also sort of forces us, when we partially twist in certain directions, to have holomorphic dependence in those other directions. Okay, so that's a constraint, a very nice constraint that comes about from supersymmetry. And also, if you look at the few variations, they don't contain the metric in those 2 directions. So it doesn't depend on the Kähler structure in those 2 directions that are holomorphic. And that's very nice. It allows us to rescale things in those two directions also. So what's nice about this, sort of partial twist is that you topologically twist in some directions, it's automatically holomorphic in those other directions. So in this case, 3 directions topological, 2 directions holomorphic. So this twist results in 4 supercharges that are scalar along V. Okay, so we have a choice to look at the different BPS sector of this twisted theory, meaning to look at, states which are annihilated by a certain subset of, these 4 scalar supercharges these 4 supercharges that are scalar along V. So they're scalar along V, so the supersymmetries are preserved when you deform V topologically. So we wish to pick a supercharge Q that is a scalar along V, okay? So which we would like to localize the theory with respect to. Okay, so what this means is, put the Lagrangian in a Q exact form, and then looking at the the contributions to supersymmetric or BPS configurations that are given by variations of the fields or supersymmetry variations of the Fermi fields to be 0. Okay, so that's exactly what we're doing. So now we shall choose a certain linear combination of 2 supercharges to be our Q. Okay, so there are many choices that you can make, but for our purposes of what we want to show, we will be making a certain choice of Q. So let's just say we make the choice of Q using the 2 supercharges of 4 here, okay, and writing it as a parameter for T here, where T is a parameter that is defined on a sphere value of parameters, okay, on CB1. In other words, they can be complex, So, but for our purposes later on, we will choose T to be -1. Okay, that will give us the desired models in the lower dimension with which we could get the results that we desire. So generally, if you consider such a supercharge, then these are the twisted supersymmetry transformations. So essentially, it's just from the original supersymmetry transformations, and then linear combination of them, and then with the fields that you see here having different spins because of the twist. So some spinor fields become scalars or spin 0, some become spin 1, and then some of the fermionic fields, the scalar fields become spin 1 and all that. So the usual sort of story for twisted theories, but now in 5 dimensions. Okay, so this is just some details here. This twist was first considered, we first studied this twist in detail in this preceding paper of ours here, which, we are still thinking about how this all relates to what we're doing right here. But as for now, we just keep it, as a discussion to talk about later on. But this is where we first considered this twist in this paper here. So, but such a twist has also been discussed conceptually by Elliott and Pestun in their paper here on Hitchin systems and supersymmetric gauge theory. So the transformations take a form that's very similar to those of the GL twist in n equals to 4 super Yang-Mills, as studied very well by Kapustin and Witten. So in fact, if you take the Riemann surface that we have, in the holomorphic directions, to R cross S1 or T2, whereby the X5 direction is S1, and if you dimensionally reduce, on S1 to reduce the 5D maximally supersymmetric Yang-Mills theory to n equals to 4 theory in 4 dimensions, you can see that it will reduce, the transformations will reduce to that of Kapustin and Witten, with the A5 becoming the R5 4 in Kapustin and Witten. So these are fields in Kapustin and Witten. Okay, so most of it is the same terminology, perhaps except for maybe this one over here, I guess. But the point is that it will reduce the Kapustin and Witten's twist and the field variations. Okay, so this is what we mean by a GL twist in 5 dimensions. It reduces to a 4-dimensional GL twist. That twist is topological in all 4 directions. Okay, so in what follows, we shall be interested in our 3 manifold being of this form. V would be an interval cross R plus, so it's a manifold with corners. Okay, and the Riemann surface here, because we want to embed, 4D Chern-Simons theory into our setup, we want it to be either a rational curve, CP1, a cylinder like this, or a torus like this. Okay, which, in the language of 4D Chern-Simons with a lattice would give you integrable systems associated with the Yangian for this one, the quantum affine and the elliptic affine algebra, which has the symmetries of the XXX spin chain, XXY, Z spin chain, XYZ spin chain. Okay. So yeah, so of course we could replace sigma with something more general, but that would involve some modifications to how we could define 4D Chern-Simons. the Lagrangian. And so we, just to keep things simple, we'll just consider the case of these three possibilities. Okay. And so if you construct this 5D GL twisted theory, that is supersymmetric, and obeys, that's consistent with everything, then you could write it in this form. Okay, so this is the Q that we're using. And just some bunch of fields here which are fermionic. So it's a Q exact form. And then with this term here, okay, this term here, and when you localize the theory to the Q invariant states, the contributions will be picked up by this term here, and that's how you see that actually this term here actually localizes to a boundary, which actually gives us 4D Chern-Simons. Okay, so that's, I'm just jumping ahead, but just so that you see from the action, you could sort of observe this already. So here our psi tilde is a real parameter. So psi, in the calculations, it's in some expression in terms of t. We have selected t equals to -1 for our purpose of finding the sigma model that we desire. If you choose t to be a different value, you get a different kind of sigma model on the other side of the reduction, as we'll talk about later on. So we have selected t equals to 1. So what essentially means, what this essentially means if we select t equals to -1 is that in this whole family of twisted theories, we're just looking at a specific one particular twisted theory in this family, this continuous family of twisted theories. Okay. So it's extremely rich. Okay, just like the GL twist in 4 dimensions, it's extremely rich. Many more things beyond geometric Langlands can be said in 4D n equals to 4 than just the usual geometric Langlands that we know. So likewise in 5 dimensions, many more things can be said, and we're just looking at t equals to -1 so that we can have a concrete result of something that's very precise. So F here is the curvature of the complex connection involving A alpha. Alpha runs from 1, 2, and 3 in the V direction. Okay, and then which is I cross, it's I, R, and R plus. And then AZ bar, these are directions on sigma. So sigma itself has a Z and Z bar coordinate. Okay, and Z is x4 plus IX5. Okay, and this is the same sign because it's a contravariant vector. So it's the indices are at the bottom. Okay, so and Z and Z bar are local complex coordinates on sigma. Okay, so of course we have boundaries. So we need to specify boundary conditions which are supersymmetric. So we have a few choices. So for our purposes, at the origin of R plus, the first boundary here, if you look, it's a strip here, first boundary here. So we pick an NS5 type boundary condition. Okay, so why we say NS5? So in our previous work, we sort of, we had a configuration of D4 branes ending on NS5. And in this case, we have not talked about it, but we could realize this is what we're studying here in terms of string theory also. So we have a D4 brane that ends on NS5 and we have a D6 brane that's intersecting the NS5. So that, if you do a t duality down, then you would end up getting something like a D3 brane intersecting NS5 and a D5, which is a corner configuration studied by some people, which allowed them to get sort of some W algebras that are in 2 dimensions. Okay, so that's roughly the inspiration or sort of the guidance that we got to pick NS5 type boundary conditions to maintain supersymmetry. So this translates to the fact that we would have these 2 conditions on the gauge fields. So this alpha tilde runs from 1 to 2, and then Q must annihilate it, so it's invariant under Q, and likewise for Z bar. And of course, being NS5 type boundary condition, the A's obey Neumann boundary conditions. Okay, so it's pretty straightforward. And of course, that's the origin of R plus, but we have to say something about what happens at infinity along the R plus. So the boundary conditions are taken to be at the infinity of R plus, X3 independent. So X3 independent meaning that's the R plus direction. X3 independent Q invariant configurations that involve a alpha tilde and a Z bar. Okay, so the Q invariant configurations, now that's understood. You want to preserve supersymmetries at the boundary. You want the action to be Q invariant. So that's, if you look at the terms that if you potentially give you non-zero Q invariant Q variations, then you want to set them to 0. About this X3 independence. So the endpoint, or not the endpoint, but we are hoping to embed 4D Chern-Simons into this 5D maximally supersymmetric Yang-Mills. And so 4D Chern-Simons, for it to be well defined, as shown by in the previous paper that we worked on geometric Langlands, which is in some sense, a higher dimensional version of what Witten did in trying to find the integration cycle over 3D Chern-Simons so that it converges analytically continued Chern-Simons. So we would need to recast our 5-dimensional theory in terms of a 1D sigma model into the space of fields, and then use the same technology that gave us a Lefschetz-Timbo, an integration cycle of the path integral of the Chern-Simons. And from that point of view, we needed the world line of the 1D sigma model was long R plus, and there was a requirement of the boundary condition of the sigma model at infinity to be X3 independent. Okay, so this is the origin of the X3 independence. Yeah, okay, so this is what we have here. So we've talked about the boundaries of R plus. So let's talk about now the boundaries of I, the other two corners here. So the boundaries of I, we can have non-pole type boundary conditions. Okay, we could choose other types of boundary conditions which are supersymmetric, but we choose a non-pole because eventually we want a Toda theory. So it is sort of well known by now in lower dimensional examples that if you want to get a Toda kind of theory, you ought to consider a non-pole type kind of boundary condition, and this is what we're going to do. So we'll consider a non-pole type boundary condition on the both ends of I, which are defined in terms of curly A, which is a complex gauge field. So these are valued in the real Lie algebra, but taken together as a complex gauge field, they can represent a gauge connection on a complex gauge bundle. Okay. So and of course the gauge fields that we're talking about ought to be Q invariant again, so as to preserve supersymmetry and to preserve the Q invariance of the action. Okay, so we'll talk a bit more about this non-pole boundary condition here. So let's do some relabeling of our coordinates. So x2, is R. Okay, so the second factor in our 5 manifold. So we'll write it as tau, and let's just redefine this convenient coordinates here. So we have this x plus and minus coordinates, and so it's a mix of this R direction and A direction in the sigma. Okay, and so then we can also define with this respect to this convenient redefinition, we can also have this definition of gauge fields. Okay, and then along I itself, the interval, okay, which is given by x1, the first factor in the 5 manifold. Okay, so we call it x1. So we can label it as sigma. As sigma, we can take it to go from 0 to pi. So non-pole type boundary condition, is defined as follows. As you come, to one end of the interval, you have a gauge field that looks like this. Okay, so essentially all components of this gauge field vanish except for the sigma component, the x1 component, and the x plus component. Okay, so the x plus component is here. Okay, so these are the two non-vanishing components if you define a non-pole type boundary condition as you go to the one end of the interval. So this H here is just the Cartan matrix of the Lie group, and then the T plus here is the following matrix here. So it's defined as follows. There's a homomorphism of SU2 into SUN, and it's chosen such that image under this homomorphism of SU2 matrix to SUN matrix, which we call T plus of the raising operator of SU2. So it takes this form. The point is there are these constants inside here, which we label as mu1, mu2, mu_n. Okay, so this is the T plus. This is how it's defined. So analogously, at the other end of the interval where sigma is pi, we also have non-pole boundary conditions, but note that they are slightly different. Okay, so here we have plus components that exist and one component that exists. Here we have the one component that exists and then the minus components, component that exists. And the T subscript minus matrix looks like this, and its values are V. Okay. Now, as I mentioned earlier on, the 5D Yang-Mills twisted action, which has a Q exact part, and the topological or the FHF part, which is not Q exact, but nonetheless Q invariant. Okay, after we put in the boundary conditions. Okay, it's Q invariant, right? And then this whole path integral would localize to that term, the non-Q exact term, and which then has a boundary contribution, and that will give us 4 Chern-Simons. Okay, so the path integral of this theory localizes the solutions of Q invariant configurations. So we're looking at Q closed but non-Q exact, so Q homology configurations, and then it reduces to the path integral of 4 Chern-Simons that looks like this. Okay, so we are looking at, so this is the integration cycle that we're talking about, which makes this 4 Chern-Simons well defined. And it's defined by Q invariant localization equations, which we have worked out in detail in our previous paper that I mentioned and cited just now on lattice models, geometric Langlands, and string theory. And so, and if you remember, there was a psi tilde earlier on where we saw in our 5D theory. So it's just being labeled as I over H bar here. So if you look at this, we actually just have one term here. So if someone is careful enough, you would sort of realize that actually we have three boundaries, right? We have one at the origin of our class, okay, four in fact, okay. One at the origin of our class, okay, and then one at the one end of the corner of I, then another one at the corner of the other I, of the other end of I, and then you have another boundary at infinity of our class, okay. So what's going on here is that of these four contributions, there's only one that survives. The one at infinity just gives us a constant factor in the path integral. So you can take it out as a phase, a constant phase, if you will, and then it doesn't change the dynamics of the theory. So the two contributions coming from the two ends of I, the boundary conditions that we have chosen set them identically to zero. Okay, so very nicely, we just have one factor here, a single contribution to 4D Chern-Simons from the boundary, from the various boundaries. Only the one at our class, the origin of our class, contributes to the path integral. Okay, so that's what we get here, a very nice result. So this integration cycle is Lefschetz-Tinvaux that ensures the convergence of the path integral. So it essentially you're integrating over the space of fields that are defined by the Q-invariant localization equations. That's not the entire space, it's just a space which ensures that the exponent behaves in such a way whereby you can integrate it over, it gives you a sensible result and it converges. Okay. So what have we done so far? We have started with 5D maximally supersymmetric Yang-Mills on this manifold here. We have done a topological holomorphic twist in the sense that these three directions are topological, these two directions are holomorphic, okay, and recast this Lagrangian here in terms of a scalar supercharge, whereby we want to know the supersymmetric configurations with respect to this scalar supercharge. In fact, more precisely, we want to look at states or operators which are Q-closed but not Q-exact, okay, of this theory here. And then we are able to localize, to these, these Q-invariant configurations to the to have the contribution coming from the non-Q-invariant part that we saw, the FHF part, and then that itself localizes onto the boundary, okay, to give us 4D Chern-Simons, as I've explained in the slide before. And so now we're up to here. Now we want to explain what happens, how we get sky here, okay. So three-dimensional Toda theory. So a 3D analog of WZW theory that's dual to 4D Chern-Simons theory can be obtained when the two topological directions of 4D Chern-Simons has a boundary. Okay, so this has been done by Ashwin Kumar, who's also a co-author of this paper. So it's in this paper called Integrable Lattice Models and Holography. So a 3D analog of WZW is dual to 4D Chern-Simons in the bulk. If the topological directions of 4D Chern-Simons has a boundary. Okay, so this is shown quite rigorously here. So something similar can be done in our current setup, where there are now not just one boundary component, but there are two boundaries on the ends of I. Okay, so we have two boundaries on the ends of I, because our 4D Chern-Simons is now defined on this. Okay, and the topological direction we're talking about in 4D Chern-Simons is I cross R. The sigma here in the terminology of Costello, Yamazaki, and Witten is the spectral curve. So we are topological in these two directions where you're supposed to put the lattice. Okay, so we are not considering lattices in I cross R now. Future work, we could consider lattices that would introduce some singularities into the modular space, Bogomolny moduli space. So, but we are just considering the very simple case of no lattice here. And so we have, so a boundary on I cross R, which is the topological direction of 4D Chern-Simons. And so we can have something similar as what was done by Ashwin Kumar in this case here with WZW. So let us focus on the boundary at sigma going to 0, so one end of I. Similar arguments can be applied to the other interval where sigma goes to pi. Okay, so via the boundary condition of A minus equals to 0. So if you look at the non-pole boundary condition, as I mentioned earlier on, at sigma tending to 0, the rest of the components of the gauge field vanish except for the x1 component and then the plus component. So naturally, this means that the A minus component is 0. Okay, and if you substitute this boundary condition to the 4D Chern-Simons at the ends of the interval, one end, then you realize that you can compute 4D Chern-Simons to be 3D WZW. Okay, It's a 3D WZW because if you look at this form here, it looks exactly like, you know, two-dimensional WZW, just that the measure is three-dimensional. Okay, so the measure is three-dimensional. Again, you have this Z coordinate here that's along sigma here, and then you have a mixed coordinate between R and sigma here. Okay, and then you have this the topological term in WZW that's one dimension higher. So it's basically a 4-form, right? Here, it's topological. Yes. Okay. Sorry, am I out of time? Yeah. Right.
You have 5 more minutes.
Oh, 5 minutes. Okay, fine. So okay, so we can compute the currents of this WZW model. Okay, likewise, if you look at what happens, you know, at the end, the other end, you know, you also can compute the currents. These are the conserved currents. Okay, you can rewrite. So for convenience, we rewrite the conserved currents into, you know, a Cartan decomposition of conserved currents. Okay, mind you that this G now we are talking about is a complex gauge group already because it descends from this curly A, which can be interpreted as complex gauge field. Okay, so because it's complex, we can do a Cartan decomposition of the J's, all right, into the, you know, the upper triangular nilpotent subgroup, the lower triangular nilpotent subgroup, the Cartan subgroup. Okay, and then if you add in the rest of the Nampo boundary conditions, we get these conditions on the fields here. And so you can see that U mu's and the V's come in because the TI's, the T plus and T minuses contain the mu's, and the T minuses contain, the T minus matrix contains the V. So you get these things here. And next we can use a Gauss decomposition of the G field in this manner, which then if you substitute this G into the expressions for J here, which contains the G's here, and then you would get this constraint. Now, this is exactly what is happening, you know, sort of is completely analogous to what happens in 2 dimensions using a Gauss decomposition, Nampo boundary conditions on WZW, and then you get this constraint here. Now, if you look at this constraint, this implies that the action of a theory which gives us this constraint is essentially this one. All right, so the corresponding action that gives us these constraints as an equation of motion takes the form of a 3D analog of 2D analytically continuous Toda theory. So it looks like this. If you do a variation equations of motion for this action here, we will get this constraint, right? So this implies that if you have Nampo boundary conditions on the 2 ends, we end up getting a 3D Toda theory. Okay, so what I didn't mention here, which is a subtlety, is we have 2 copies, you know, on 2 ends, okay, which gives us a set, a pair of constraints. And these pair of constraints must conspire, you know, to give us this final result, which we can deduce to be 3D Toda theory when we shrink down the interval. Okay, so that's the important part. We need 2 ends to give us, you know, a pair of constraints that will then eventually lead us to this when we shrink the interval down. Okay. So, and from this 3D Toda theory, we would be able to get, you know, 3D W algebras in the following sense. Okay, so we could rewrite the Cartan matrix here, you know, the inverse of it as gamma I. And then you can see that this 3D Toda Lagrangian, you know, this 3D Toda theory is invariant under coordinate transformations and transformations of I. So as with Liouville theory and Toda theory in 2 dimensions, you know, you have this extra term here because of the exponent in the Lagrangian. And then you can compute the Noether current, you know, of this 3-dimensional Toda theory. It takes this form, it's conserved, and it doesn't depend on the x minus directions. Okay, so right, so what we're going to show now is that you have a W algebra, a 3-dimensional W algebra coming up from this 3-dimensional Toda theory. So let's just go to the simplest case of G equals SL2C, where the Cartan matrix is just a 1-by-1 matrix, and the value is 2. Okay, and then we choose x minus to be a temporal direction, and write x plus to be zeta. And then, you know, we could use an equivalent gauge 3D WZW model. That's this equivalent model is actually a 3-dimensional version of the Greenfeld-Sokolov reduction in 2 dimensions. Where you gauge a WZW model, you can get, you know, a stress tensor for the Toda theory. So it's the same thing here. So we can rewrite theta as T minus del J. This part comes about because you're gauging it. And if you look at this T, it looks like a regular stress tensor of WZW model, which comes from a Sugawara construction of stress tensors or high spin stress tensors that come from just contracting the currents. Okay, so and then we can derive the symplectic form on the phase space of this model and compute the Poisson brackets of the commutators between the stress tensor. Yeah.
Minute, please.
Okay. Right. Okay. And you quantize it, okay, using Moya quantization as is shown here, and then you can see you can get, you know, this structure here. And so this is a 3D analog of the quantum Virasoro algebra. So we can do this for, you know, higher spins by adding more J's into it using the Sugar-Brown construction. And in this way, we will be able to get 3D W algebras from 3D Toda theory, okay? And so you can see that it has a holomorphic dependence on sigma here, on the Z. And then at the same time, you know, there is this factor here that appears. It's very interesting. We have a singularity along the spectral curve plane. And the origins of such a factor can be attributed to the fact that you are coming from a boundary theory of a 4D Chern-Simons theory as holomorphic along sigma, okay? If we choose x plus to be the temporal direction, we'll get another copy. So it means that this choice of the temporal direction, you know, is you're free to choose x minus or x plus, you still get the same thing. So that's nice. So we have found this part here. So in the few seconds that I have left, I guess, I'll explain how we get this, okay? So how we get a sigma model. So, okay, so we are, as I mentioned, we are topological in these three directions in the 5D theory and holomorphic in this. So what we could do is to essentially scale down this direction here, okay, by scale invariance, and then while blowing up I cross R plus. Okay, so when we do that, we end up getting a 2D sigma model, on I cross R plus. As I mentioned earlier on in the talk, in the beginning of the talk, that if you look at the terms that you, if you want actions to remain finite, there's some conditions on the fields, and these are the conditions. And these conditions are actually nothing but the Bogomolny equations on R cross sigma. Okay, and then from the resulting action itself in 2 dimensions now, because you're scaling down metrics in 3 directions, you will see that, you know, accompanying the del phi term that comes from F star F term of the 5-dimensional theory is this the target space metric, okay, of the sigma model. Okay, it looks like this. Okay, and this is the metric on the moduli space of Bogomolny equations. And then you also have a symplectic structure that accompanies the A model as a pullback of the worldsheet of I cross R plus. And then we know from the fact that we've used T equals to -1 and also the expression for W here, omega here, that we have an A model in complex structure K, okay? Because the Bogomolny moduli space is hyperkähler, it has I, J, K complex structures, then you can have A models in different kinds of complex structure. And in this case, we have A model in K. And so what happens is that, you know, we have boundary conditions. We have 2 types, if you remember. So we have the NS5 type boundary condition at the origin of R plus, with Nonpotential type boundary condition at the 2 ends of I. And this results in co-isotropic, space-fading co-isotropic A branes on the origin of R plus. And then Lagrangian branes, which are analogs of branes of opus in Hitchin moduli space. They are analogs of branes of opus in Hitchin space on the 2 ends of I, okay? So we end up having a sigma model that looks like this, okay? And what we're gonna do, since the sigma model is topological, is to pinch the corners here like this, such that we have, you know, a configuration that looks like 3 strings coming in the vertex. Okay, so for us to compute the physical states of our sigma model would be to compute the physical states of these 3 different strings. Okay, so if you compute just the physical states of the string here, the B over prime string, then you realize that, you know, the Lagrangian branes of B over prime only intersect at a point, so they just give you 1 state and the physical states, the Q cohomology states, are actually ground states, and you just give 1 state. Okay, but to find more states, you have to consider. Okay, so right. Okay, I'm sorry. Maybe just half a minute. Is that okay? Just so I can finish up. Yeah. All right. Thanks. Okay. So yeah. So you want to compute more states from the other strings here, and the other strings give us states that look like this. Okay, they are holomorphic sections of the canonical line bundle on the this Bogomolny moduli space. Okay, so on the branes on the Bogomolny moduli space. Okay, so and so we want to understand. Okay, so these states, we want to understand what these states are. So these states are states of strings that are BO per BC strings, right? And if you add them with BC strings, okay, you can see they are module for BC strings. But the algebra of BC strings are just the quantized algebra of holomorphic functions on the Bogomolny space. Therefore, the space of states that we are looking at, you know, from the A model, they are modules for the quantized algebra of holomorphic functions on MB. Okay, so in effect, by, you know, 2, you know, equivalent reductions, you know, that do not change the Q cohomology of the master theory, we have a 3D Toda theory on R cross sigma on one side and a 2D A model on the other side. And then, so if we are comparing the states of what we are getting on one side and the other side, you get modules of 3D algebra defined on this, being equivalent to these holomorphic sections that are the states of these open strings between B open branes and BC branes. And then and we know, as we have shown, that these states here are modules for the quantized algebra of J-holomorphic functions, which then means that modules of 3D W algebra are also modules for the quantized algebra of J-holomorphic functions on ND. Okay, so to conclude, we have shown that 3D Toda theory and 2D A model on Borgomoni moduli space are dual to each other. We have found that modules of 3D W algebra are modules for quantized algebras of holomorphic functions on the Borgomoni moduli space. Now, the crucial ingredient is the fact that we have a 5D n equals 2 supersymmetric Yang-Mills theory, which admits a partial twist that is topological holomorphic and analogous to the GL twist of 4D n equals to 4 super Yang-Mills. Now, so in future work, what we want to do is to talk about a GL twist for a high dimensional supersymmetric Yang-Mills theory, like 6D maybe, n equals to 1,160, and then we do a partial twist. In this case, in 6 dimensions, the number of directions that you can have to be topological becomes even less now. So instead of just 3 directions being topological, we can only have 2 directions which are topological. Then you have 4 directions or 2 planes which are holomorphic in this case. And we are expecting to get something like a 4D kind of 4D analog of Toda theory, which gives us 4D W algebras. And instead of Borgomoni equations, just like from Hitchens we get the Borgomoni equations, we are expecting to get quantized algebra of holomorphic functions on the moduli space of instantons. So there's something which we want to investigate in future. Okay, thank you for your attention. I'm sorry I exceeded the time. Thanks for your patience.
Thank you very much. Maybe we can all unmute and start the speaker.
Do I still share my screen?
So we'll start with Edward Witten. Please unmute.
Yeah, I have more a comment than a question. So there's a puzzle to me about Costello's 4D Chern-Simons theory. If you look at it non-perturbatively, the R matrix has poles, which aren't quite where you'd expect them to be classically. They're shifted from there by an amount of order h bar. And in perturbation theory, you don't really see this. You can see higher order poles, order by order perturbation theory. The position of the poles isn't shifted, but their order is increased. But non-perturbatively, definitely, the position of the poles is shifted. And this is an effect that one should try to understand in a non-perturbative theory, although you can't really understand it in a perturbative theory. I'm kind of puzzled about how it is, so I can't say more than that.
Please unmute. You're on mute, Meng-Chwan.
Right, sorry. Okay. Sorry, guys, man. Yeah, so, okay. So, so that would, for us to sort of think about this a little bit deeper, we would need to generalize what we have here to include Wilson lines in the, and the lattice in 4D Chern-Simons. And in this case here, we are just starting for 4D Chern-Simons without a lattice. Yeah, so we are not putting operators inside. Yeah.
You can treat the Wilson lines just as observables.
Oh, yeah.
So
okay.
you literally can just put them in the boundary and do exactly the same thing. So your setup is adequate to ask the question.
Okay.
I don't know what the answer is.
Okay. Okay, we'll think about it.
Kumran Bafa?
Yes, thank you. Nice talk. I have a question about the, as you mentioned in the AGT correspondence, you get a map from a Riemann surface to the Toda theory on it when you want to compute the partition functions in the 4D theory. So it's natural to ask whether in your case, if you do the same thing on the 3 dimensions, whether your 3D Toda has anything to do with the partition function of the corresponding 3D theory, is it?
The corresponding partition function of a 3D. Okay, so the point is this: the sort of the generalization of AGT in our case. So we were sort of inspired to find, in some sense, a generalization of the AGT result by Nekrasov and Witten, which relates Hitchens moduli space with the W algebras in 2 dimensions. So ours is, in some sense, a higher dimensional version of that. But it's not clear to us right now at this point how we could sort of view this result as a higher dimensional generalization of the AGT. So in terms of the partition function, if you are asking, the things that we can say concretely are just partition function of, let's say, the 2D A model. the 5D model itself, you know, and the 3D Toda theory itself. So that's all we can say. But I think you're asking about something different.
Well, I'm saying that if I'm just pushing your analogy, if your analogy was the AGT gives you to the Toda theory, and if you repeat the same thing with one higher dimension, and the right answer you get 3D Toda, what are you answering? You're answering a 3D
Yeah. So yeah.
Twist of
Right. So there's no omega deformation in this case of the 5D theory. So I mean, if you look at AGT, it's 4D n equals to 2 with omega deformation. So we are 5 dimensions. One dimension higher, we have more supersymmetries. We're not looking at 5D n equals to 1. So if you look at AGT, the 4D theory that you're studying starts with 5D n equals to 1, and then you sort of do the omega deformation you compactify it on a circle, and then you talk about planes that go around the circle and picking up a rotation. And that starts with 5D n equals to 1. So it's not exactly the same. So I can't really say something concrete of how it would be for a 5-dimensional n equals to 1 AGT partition function, if you will. I think maybe that was your question.
No, I'm not asking 5D partition. No, I'm not asking that. I'm starting from 6D and going to 3D.
Oh, 6D going to 3D. So your 6D is what 6D theory you're talking about? 2,0 or the 1,1?
2,0. AD 2,0 theory on a three-dimensional manifold, just like the AGT was 2,0 AD theory on surface.
So if you start, okay, so if you start with 2,0 and you compactify in 3 directions, you could get, you know, 3-dimensional Chern-Simons, or you could get 3D n equals to 2 superconformal field theory, depending on how you compactify it.
And the question is, what's the partition function of that in terms of it? Is this related to some Toda theory on the intermediate manifold?
Okay, let me think about it. So we would have to add a circle to 5D n equals to 2 from where we started. And if you compactify it in 3 directions, it's the same as like going down to our 3D Toda theory. Yeah, perhaps, possibly. Yes, yep, that's right. It's possible. So you could compute. Yeah, you're right. So we could compute, if we add a circle to our 5D n equals to 2 partially twisted theory, that gives us, you know, some connection to 2,0. And then if we compactify 3 directions from there, which is the same as compactify 2 directions like what we're doing now to the 3D Toda theory from 5D. Yeah, you could. There could be some relationship to that. That's right. Yeah.
Okay, thank you.
I don't see any more hands, but there is a question in the chat. Nathan Steinberg asks, is it important that the theory is not renormalizable? It cannot even be embedded in UV in a 5D SCFT. Do you have any comments on that?
This theory is not reliable. Yeah, it can be embedded into 2,0 basically. Yeah, so we can look at it as 2,0 on a circle, and then you get 5D n equals to 2. Yeah, so from that point of view, it's okay.
All right, if there are no further questions, let's thank the speaker again.